Grade 12 Physics, Energy and Momentum, Note number 7. Elastic collisions. In the previous note, we looked at elastic collisions. We know that that's when two objects bounce off one another. But here we're going to look at a special property that they have compared to the other collisions. Elastic collisions conserve both momentum and kinetic energy. Inelastic and explosion collisions only conserve momentum. They don't conserve kinetic energy at all. This is just a property of nature. So what we can do is we can use this feature to derive two equations that'll help us calculate the final velocity of an object. We're going to do it for a special case where basically we have one object at rest and a second object is coming in to make that elastic collision with it. It doesn't matter what their masses are, we'll look at different properties for that, but there's basically the scenario there. One object's at rest, the other one's moving. In class we'll make these derivations, but the two equations that we're going to deal with are going to be labeled here below. The final velocity of that first object, so the shaded one, is going to be equal to the difference of their masses divided by the sum of their masses multiplied by that initial first velocity. The final velocity of the second object is going to be equal to 2m1 divided by the sum of the masses multiplied by that initial first velocity of that first object. So let's test these two equations and make sure that they make sense and that the solutions that they produce make sense. Let's do it for a case where m1 equals m2, so the two objects hitting together are of the same masses. So we can just call that mass m if they're the same. So putting them in the equation, we get m subtract m divided by m plus m. So the final velocity of that first object after the collision is going to be rest. It's going to be 0. Let's see what the second one is. Here we have 2m divided by m plus m. We're going to get a simplification in the middle, and it says the final velocity of that second object is going to equal to the initial velocity of the first object. So really what's happening here is the momentum of that first object is being totally transferred to the second object in the collision. We'll do a demonstration on that in class. So here, now let's do a second case where the mass of m1 is a heck of a lot bigger than the mass of m2. So in that case, we can pretty much assume m2 to be 0. If we put zeros in the equation, let's see what happens. The final velocity of the first object ends up being its initial velocity. So this big ball that's going to come in and hit the smaller one, it's going to act like there was no effect whatsoever and it's going to keep going. The final velocity of that second object, if we put our values in, we get a simplification, and we find that its final velocity is going to be twice the velocity of that first object. So that small ball is going to bounce off the big one at twice the velocity that the big one came in with. And we'll do a demonstration in class on that as well. Last case here, let's say m1 is a lot smaller than m2, so here m1 is pretty much going to be 0. Let's test that in our equations. So here the small ball is coming in to hit the big one. We get a simplification here. It's going to bounce off with a velocity negative of its initial velocity. So that big one really, it's just acting sort of as a wall, and that small ball is going to bounce off of it and head straight back. The velocity of that big object, if we put it in, ends up being 0, so it's unaffected by the collision.